Bon, je vais faire, I'll speak in English because I prepare the slides in English and I'm with an English mindset, in fact. And in addition, since the presentation is recorded, I would like to share it with some colleagues in America and Canada. So thank you very much for the organization of this symposium, because it's very interesting to listen to people with different backgrounds, to hear some philosophy here. And when we are interested, since we are interested in understanding the immune system, it's quite important to listen to philosophers, because they can give us many ideas. And it was also very interesting to hear to the physicists this morning. And I think I will try to use one argument he proposed this morning. Anyway, so this talk is in continuation of Veronique's presentation. And it's a joint work with Veronique, Erwan, and myself. And our purpose is to provide mathematical models of receptors in biological immune systems. I should say human immune systems. I will focus on human immune systems. I'll go further than what the title suggests. In fact, because in the talk, I will involve cells as well. And I will also involve memory, because memory and degeneracy are two crucial properties of immune systems. Okay, so I will give our motivation, and the story afterwards can be summarized quite rapidly, because receptors and cells are very important examples of what we call biological holons. So Veronique used already this term. I use it again. I gave a kind of definition of this concept later on, but I think that at this stage, it's sufficient to remember that a holon is a concept that makes it possible to account for the idea that the immune system has a fractal-like structure. And I would say, regarding the presentation of this morning, a fractal modulated structure. So it's not exactly a fractal structure, but it looks like a fractal structure. So I will come back to this point later on, but at this stage, it's sufficient. And we want to come up with mathematical models. So we have to move from the concept of holon, which is a very nice concept indeed, to a mathematical object, an appropriate mathematical object that makes it possible to model holons, to make computations on the basis of holons. And so the mathematical object we propose is the discrete dynamical system. Perhaps there are some other models, but this one seems quite interesting, quite relevant. And since degeneracy and memory are key in understanding the immune system, we want to verify that indeed with our discrete dynamical systems, we can make memory emerge. And we also want to look at degeneracy of such systems. And we will see that indeed we have mathematical results that support the idea that discrete dynamical systems have memory and make degeneracy. It can be based on degeneracy. Okay, so our motivation is very simple, in fact. We are struck by the fact that the immune system is capable of detecting and dealing with perturbations while preserving our organism and while maintaining our health status. And in fact, despite all the exponential increase of allergens and chemical antigens, despite these new infections we have been experiencing for more than 1 year now. So despite all these adverse conditions, the immune system can manage all these functions. So how can it do that? So it's a fundamental question, of course, and there are many researchers who are we'll tackle this question. What's the difference between our approach and other ones? I would say, by and large, that current approaches in biology and immunology are mainly empirical. And in contrast, our purpose is theoretical, with a long-term purpose. And so we want to come up with mathematical models, mathematical foundations, and I would say mathematical axioms to make it possible to test, simulate, get better insight into the behavior of the immune system. And if I use the term axioms, it's because in general in mathematics, when we are provided with axioms, we are also provided with an algebras that make it possible to make computations. And if we can make computations, we can implement these computations in a computer. So it means that we can run simulations, we can make numerical analysis. So we can actually help biologists and physicians to test their strategies, their medications, with respect in a kind of in silico biology platform. That's the ultimate purpose. And of course, that's a long-term purpose. In fact, this purpose is somewhat supported by what Philip Kowalski wrote in 2014, when in his book, he claimed that there is some need for mathematics to make progress in the systematic study of life. And so this book was really inspiring for me. And we started discussing with Veronique in 2015 or 2016, something like that. So we need a starting point. And if we want to understand the immune system organization, its development and its disorganization through aging and diseases, we have to get some insight into it. And so it's a complex system. Here you have a list of features enhancing this complexity, emphasizing this complexity. And our starting point is the fact that if you scrutinize the immune system thoroughly, and I use the same pictures as Veronique, you come up with the idea that at each level, at each scale of the immune system, you face networks of interacting multi-reactive and autoreactive cells. And you face also redundant interacting receptors. And these networks have a very high connectivity. And as I mentioned it at the beginning of the talk, we think that the appropriate notion to encompass this behavior is the concept of how long. And so our work hypothesis is that at each scale of the immune system, we have to deal with a network of interacting biological how longs. So in this sequel, I'll say how long. I'll drop biological to alleviate the terminology. So this is our work hypothesis. But so what is a how long, in fact? So let's have a definition of how long derived from Kessler's point of view. So a how long is a rule, which is itself included in a vaster rule. So here you have the idea that you have this idea of a fractal-like structure through the notion of a how long. And a how long is quite autonomous. It can deal with events without authorization or instruction from any monitor. And it's also, it is also part of a communication network because it communicates with other how longs at its level, but also with superordinates and subordinates. So this is a very nice concept. So now let's try to go to cast this concept into a mathematical framework. And to do that, we have to make some bottom-up work. And so we have to discuss with biologists. And it turns out that cells, and I should say, I'll say also receptors, basically behave as dynamical systems. They are dynamical systems. They undergo, they receive input signals. These input signals trigger some change in these entities, and with this change, you have output signals. Okay, and so we are going to focus on dynamical systems, and more precisely on discrete dynamical systems. And why discrete? It means that we are going to study these dynamical systems in discrete time and not in continuous time, just because we want a computational or computable model. So if we use a computer, we have to deal with discrete time dynamical systems. So regarding this story, it starts with a very nice paper written by David Spivak. In this paper, David uses a very general definition of discrete dynamical system. I say DDS to shorten the vocabulary. So it deals with, it uses such a definition. And so here, this slide summarizes the axiomatic used by David. So at the beginning, you have a box. And this box is equipped with input ports and output ports. X in and X out. So X in will designate the set of all input signals that can be presented to the box. And X out will stand for the set of output signals of this box. So given a box specified by these two sets, with a discrete dynamical system is a triple S and XD, an update function, and a readout function. So S and XD is the set of states, and the state is the memory of the system. In the theory, S and XD can be any set. The update function, its role is to update the state of the system. And it performs this task by taking the input signal into account, taking the current state of the system into account, and on the basis of these two quantities, it outcomes a new state. And the readout function outputs a signal on the basis of the new state of the system only. Okay, so this is a basic model. And as I mentioned before, when you have some good axioms, you have some algebra with that. And that's exactly what happened with David. In this paper, he presents an algebra, which is based on a matrix arithmetic, in fact, that makes it possible to compose all these discrete systems. So here you have two discrete systems, discrete dynamical systems in parallel. Here you have a serial composition. Here you have something more complicated with the feedback. And I like this one because here, this figure illustrates the fact that we have a fractal-like structure. You see, we have at each scale of this complex composition, we have dynamical systems wired together. And this box is in turn wired to this one, and so on. And so we can complexify the construction at will if we want. Okay? And so with this nice algebra, David was capable to calculate the steady states of of dynamical systems resulting from such wiring. But we go further, in fact. We go further because, as I told you, we want to study the memory of such discrete dynamic systems. So we have the internal memory of these systems via the state. But can we make emerge memory by wiring all these dynamical systems? And the answer is yes. And that's what we published in 2019 with this title. This is the title of the paper. And so let's summarize the finding. So here, as a gentle reminder, I rewritten very briefly the definition of the DDS. And to establish our results, we need 3 additional definitions. So we have the notion of memoryless DDS. So it's a DDS, but in this case, the update function depends on the input signal only. It discards any influence from the state of the system. And so a memoryless system is essentially reactive. It reacts to a signal, to an input signal. We have now the finite DDS. So the finite DDS may have some memory or not. In fact, the finite DDS is characterized by the fact that its set of states is finite. And among all finite DDS that you can imagine, you have the Boolean DDS. The Boolean DDS is simply a finite DDS with whose set of states reduced to 0, 1. Okay, these are the players, and with these definitions, we can state the following results. Green is not very nice, very nice. Sorry. So I will focus mainly because I don't have. Well, okay, I think I have time enough, but in order to save time, I will focus on the second result mainly because it's the case of a finite DDS that this result addresses, and we are interested in finite DDS because for computational reasons. So any finite DDS, so any discrete dynamical system with a finite set of states can be obtained by wiring together memoryless Boolean discrete dynamical systems. And whatever the update function and the readout function may be, okay? So we have a very general result that to a certain extent is an extension of what you know, of course. It's the fact that a computer is made of transistors. So you may have a very complex machine with a very big memory built up via very basic Boolean transistors. So, but the result is more general. It involves computers. It includes computer, but since we don't have to choose specific update functions and readout functions, it's very general. And so as a take-home message, you can remember finally that memory emerges from communications and interactions. And that matches exactly what Veronique's findings through experiments. So that's very important. So it supports the idea that this model is not that bad. Okay, but we have a question now. I told you that we can choose any update function, any readout function, great. But isn't it possible that among all the possible choices we have, there isn't some better functions than others? Perhaps optimal functions, perhaps optimal readout and update functions. As if you pose a question like that to Veronique, I think she would answer, nature achieves selection, but seeks no optimality. And even optimality can be detrimental to life. And I would answer, as a mathematical engineer, I like optimality. I try to find optimal solutions. That's normal. And in as much as there are so many criteria for optimality, that perhaps the actual question is to find the correct, the appropriate criterion for optimality. And if we find this criterion, we can reconcile degeneracy and optimality. And Veronique would say, I think, and she's right, don't forget that if each receptor were optimal in the sense that it would be designed to react to one specific signal only, we would be 60 times bigger than we are. And so we would have a very big problem of sustainability. So in order to avoid this sustainability issue, we may think that nature has opted for a smart solution, which is degeneracy. And indeed, receptors are degenerate. They are not attuned to one specific signal, but to a broad class of signals. And we have R1 who would say, okay, yes, I'm here. And it's good because this degeneracy principle was formalized by what is called the multiplicity principle in a book written by André Rosman and Jean-Paul von Bomersch. And so I can add now that we have also statistical tests that can play the role of optimal update functions in terms of robustness. If we think of in terms of robustness, we can come up with update functions that are optimally robust. So let's try to mix all that and to interface all this knowledge. And that's what we achieved in a paper. And I will summarize the findings of this paper in a few slides. But first, I want to come back to the notion of degeneracy, because it's a very important notion, and it's good to have its definition given by Edelman and Gary. So it's a notion introduced in 2001. The multiplicity principle was established in 2007. In the sequel, I think I will stick to the term degeneracy. I won't use the term multiplicity principle, just in order to alleviate the terminology and to stick to one piece of vocabulary, okay? But at some places, I should use multiplicity principle instead of degeneracy. So degeneracy is a biological notion, and it's the ability of elements that are structurally different to perform the same function or yield the same output. It's a kind of functional redundancy. It means that you may have two systems that are designed completely differently, that may have been designed for achieving some ultimately some different functions, but they can work for the other in case the other fails. They can be surrogates of each other, and that's great. And this degeneracy principle goes hand in hand with complexity and also natural selection. And it also involves not only the immune system, but all living organisms, and of course, the brain as well. So that's degeneracy principle. And there is now another key point, quite surprising, in fact, for a mathematician or a physicist. And that point was underlined by Philip Kurisky again in his book. He wrote that, in fact, biology is still in a rather qualitative phase of its development and not very quantitative phase. And it has to take into account the energetic dimension of the problem. So surprisingly enough, biologists are not that motivated or motivated by energy, except Véronique, in fact. But that's true, that's very surprising. And so we'll find again this energy in what follows. So now I can summarize our work. And this work starts with a mathematical model. At the input, at the input of a discrete dynamical system, we are expecting some signal theta. This is a signal of interest. But there won't be theta alone. There may be some interference delta with this signal. So at the input of the DDS, you have theta and delta. But they are not alone. There is also some noise, because with any sensor, you have internal noise. So we can see interference as external noise, something that is going to be captured by the sensor. But the sensor, once it has captured theta plus delta, it adds some noise, some corrupting noise. And so at the end, the input signal is X equal to theta plus delta plus W, signal plus interference plus noise. And we have to deal with that. And so the question is whether there is some signal or not when we observe this X. If we state the problem like that, we have a very well-known theoretical framework drawn from statistics. It's the Niemann-Pearson approach. 1937 or something like that. And the Niemann-Pearson approach makes it possible to decide whether theta is zero or not, somehow. And in fact, it proceeds by trying to answer the question on whether the observation results more likely from the presence of theta or from its absence. And from this framework, we can derive an update function for our discrete dynamical system. And this update function has its form. It's going to compare what we call the likelihood ratio. L means likelihood, the likelihood ratio of the observation to a threshold. So it's not necessary to detail what the likelihood ratio is. It encompasses, it encapsulates the idea written above. Does the observation result more likely from the presence or from the absence of theta? And if this likelihood is big enough, we change state. Otherwise, we stay in the same state. And there is an alternative to this approach. And this alternative is what we call the random distortion testing approach. And in this random distortion testing approach, the question we try to answer is whether theta deviates by too much from zero or not. You see, there is a slight difference. We don't try to detect whether theta is present or not. We try to know whether theta deviates from zero or not, deviates from significantly from zero or not. So there is a slight change of point of view. And the expression of this update function is this one. And here you find energy again. You compare the energy, which is quite natural. In fact, that's something you would say, you would do naturally. You compare the energy to a threshold. If the energy is big enough, you go for state one. Otherwise, you go for state zero. So now if we compare through this table the behavior of these two types of update functions, we have the following. The Niemann-Pearson update function is based on likelihood. The RDT update function is based on energy. That's more biology friendly. The NP update function is optimal. Yes, indeed, it's optimal in absence of interference. That's the key point. If there is no interference, NP is the best. Well, but there are interferences. And in contrast, the RDT update function is optimal even in presence of interferences. And that's due to the fact that these two approaches try to optimize different criteria. And it turns out that because of this difference, the NP update function is absolutely not reliable in presence of interference. It doesn't work. Whereas the RDT update function keeps on working because it's robust to interferences. Its criterion involves robustness in its own design. And these two functions share the same property. Sorry, it's not, look at that first. They share the same property, that is, they tend to the ideal update function. That is the update function that would change state without any error. And this ideal update function would be obtained asymptotically if we had, if the dimension of the observation were infinite. And mathematically, they both tend to this ideal update function. So when we look at this table, we can conclude that NP and RDT update functions satisfy degeneracy. I should have written multiplicity principle. Okay, I skip this one because perhaps I run out of time and I want to stick to the available amount of time. So now let's go to the conclusions. So we have a model of hollow for cells and immunoreceptors as discrete dynamical systems. And here you have further details supporting this idea from the biologic point of view. We have also a theory to prove that memory can emerge from a network of memoryless Boolean dynamical systems. Okay. Well, we have also pinpointed two families of update functions that satisfy degeneracy. Okay, and we can even derive or draw from this result that it's reasonable to conjecture that NP update functions are good candidates to model receptors of cells in the innate immune system, because the innate immune system is more dedicated to specific signals. In contrast, the RDT update functions are better candidates in the adaptive immune system because they make it possible to deal with ranges of different signals, but that are somehow alike, but different in any case. Okay, that's great. We are very happy with that. But the question is, all this theory, does it provide us with metaphors, with mere metaphors, or actual models? And we don't have the answer yet. And that's the reason why I asked Veronique, I put the question about the amount of work to do experiments, because one issue we have now is to experimentally challenge the theory. So we have data, we have ordinary differential equations to describe data. We have agent-based models. Veronique was able to fit experimental results with numerical results. Can we do the same with this kind of model? That's the question. I haven't spoken that much about readout functions, and that's something we must involve in the theory. And the question we have also is, since the theory seems quite general, would it be possible to involve more elementary components such as enzyme? Okay, so that's it for the talk. And okay, thank you for visiting the Holon Galaxy with us.